This video contains a brief reminder of static optimization for those economists who already know it, and for those who don't know it already, it should be a brief introduction such that you can work with these methods afterwards. A good textbook treatment of this topic can be found in the book by Dixit, Optimization in Economic Theory, Oxford University Press, the second edition. Before we start, some clarifications up front. First, please remember that models should be an abstraction from reality, so simplifying is their aim, as we already know from the video on the purpose of economic models. Now, most economic models involve optimization in some form or another, so that either households maximize their utility or firms minimize their costs. But there are many other ways of optimization in economic models that you can find. The good thing is that the mathematical structure of these models is rather similar. Now, of course, economists do not believe that consumers sit in front of the supermarket shelves and solve the Lagrangians and Hamiltonians associated with optimization problems. But the optimality rules that you can derive by means of these methods are often surprisingly close actually to the observed behavior. And as we will see, these optimality rules also have a straightforward intuitive interpretation. Now this video, as I said, contains a brief introduction to static optimization for economists, or for those who already know these methods. It should be a reminder and repetition. And for dynamic optimization, please see the corresponding other videos in the playlists that I have uploaded. As far as the notation and the problem statement are concerned, we use vector matrix notation in most of this chapter, and we start with a two-dimensional case so that we have two goods or two production factors at the beginning, such that the vector x that we use contains two elements, x1 and x2. In the context of a utility maximization problem, that would mean consumption good 1 and consumption good 2. Now, the function to be maximized, or the so-called objective function, is denoted by f of x. So that's a function of the input vectors that we have. This can either be, again, a utility function if you maximize utility of consumers. It could be a profit function if you maximize profits of firms. It could be a cost function if the firms minimize their costs, and so on and so forth. So there are many different functions that you can imagine in these contexts. Then there is a constraint, and the constraint is denoted by g of x is equal to c. And this is typically a budget constraint in case of household utility maximization, or in case of the maximization of firms, it could be the production possibility frontier that you can produce with the given production factors and technology at hand. So now in this setting, what we want to find is a vector that we denote by x bar that maximizes the objective function f of x subject to the constraint. So the constraint must be fulfilled and the objective function must be maximized, and the vector that achieves that is denoted by x bar. And in the following, we will look at a certain cookbook procedure that can be used to solve these problems in general. And the advantage of these cookbook procedures is that you don't need to have a thorough mathematical grasp of the proofs of why it works, but you just apply them step by step to the problems that you face in economics, and then usually you can come up with a solution, and I will also tell you when you cannot come up with a solution or when the methods are insufficient to determine the global solution to the problem, the global minimum or the global maximum, and what you can do to determine the global minimum and the global maximum if you have multiple solutions. Now the first step in this cookbook procedure is to define the so-called Lagrangian function, which is a function of the choice variable, so the vector x, and the so-called Lagrange multiplier that has the interpretation of the value by which the objective function increases if the constraint is slightly relaxed. Now the Lagrange function itself is defined as the objective function plus the Lagrange multiplier times the constraint, where we have the right-hand side of the constraint here minus the left-hand side of the constraint. That's That's the definition of the Lagrangian function. And then in the second step, what one has to do according to the theorem of Lagrange to derive the optimum is to calculate the so-called first order conditions or necessary first order conditions for a maximum or a minimum of the objective function. And this is that if a certain choice variable x bar maximizes the objective function and at the same time it satisfies the constraint, where the constraint should be binding at least for one element, that's the so-called constraint qualification, then it has to hold that the derivative of the Lagrange function with respect to the choice variables, to each of them, in our case of two, we have two choice variables, so we have two derivatives of the Lagrangian function with respect to the two choice variables. This has to be equal to 0. So the Lagrange function has to attain a maximum or a minimum, which is the statement that the derivative of the Lagrangian is equal to 0, and the derivative of the Lagrangian with respect to the Lagrange multiplier has to be 0, and this basically replicates the constraint. So the constraint has to hold for the optimal solution, and the Lagrangian function itself should be at an optimum, either in maximization it's a maximum or in minimization it's a minimum, and at this minimum or at this maximum the function has the property that the derivative is equal to 0 because the function value itself does not change anymore. Now this method provides a system, in this case for two choice variables we have three equations and three unknowns, namely the two choice variables and the Lagrange multiplier. And this system of three equations and three unknowns can in general be solved for the optimal choices and the Lagrange multiplier, which, as we said before, is then the value by which the objective function would increase or decrease for a slight relaxation of the constraint. So this sounds rather technical at first glance, but the good thing is it has a very straightforward mathematical and graphical interpretation on the one hand, but also an economic interpretation, and we can put it into everyday language. So the intuitive interpretation of the result of Lagrange's theorem is really accessible. We start here with the mathematical interpretation, and that states that at the optimal choice, a slight reallocation between the choice variables that still fulfills the side constraint must leave the Lagrangian function and therefore the objective function unchanged. Now this means nothing else than if we make an optimal choice, and at this optimal choice we decide to choose a little bit more of x2, say, instead of x1, and the constraint is still fulfilled, that means that we have to reduce consumption of x1 by a little bit, then after this reallocation, we must not be able to get a higher objective function, a higher utility level, if it's a utility maximization problem. Otherwise, of course, the initial choice would not have been optimal in the first place. So if a slight reallocation increases the Lagrangian function or increases the objective function, then the initial choice was not optimal to begin with. And the mathematical result that the derivative of the Lagrangian function has to be 0 at the choice variable, that ensures that this is actually the case. So we cannot increase the Lagrange function further by changing the choice variable. We can illustrate this graphically in a simplified depiction where we just have observed one choice variable. Let's say we keep the other fixed. Now here we would have the value of the Lagrange function for a well-behaved Lagrangian function that is strictly concave in this case, so it increases first and then increases later on for higher values of x. And we see that this has a maximum in this case here at this point, basically, where the function is the highest value. And exactly at this point, of course, the derivative of the Lagrangian function with respect to x is 0, because exactly at this point, the function is flat. And that's the reason why the first derivative with respect to the choice variable has to be equal to 0. Now we see that at this point, a slight change in the choice variable must not be able to increase the objective function further, because otherwise the optimal, or the supposedly optimal choice would not have been optimal in the first place. And of course, the same reasoning holds for a minimization problem. In this case, it's just that the objective function at the optimal point, it must not be able to decrease it any further by changing the choice variable. So that's the mathematical and graphical interpretation. Now, the economic interpretation is that actually at the optimal choice, an individual would equalize the marginal contribution of an additional unit of C, so of a marginal relaxation of the constraint on the objective function. So for example, if we are in the case of utility maximization, where the objective function is the utility function u of x, then the result of the first order conditions of such a maximization problem would be that individuals would consume at the point where the marginal utility of consuming good 1 divided by its price is equal to the marginal utility of consuming good 2 divided by its price, and that is equal to the Lagrange multiplier lambda. So by which the value by which the objective function increases if the constraint is slightly relaxed. What does this mean actually? So it means that if we get a little bit more money, we would spend it in a way that basically the additional unit of money buys us the same increase in utility across all the goods for which we spend money. And this is only the case if the marginal utility with respect to a certain good divided by its price is equal across all the goods that we can buy. So that would be the optimal choice. If for one of the goods that we can buy, an increase in spending on this good would lead to a higher marginal utility divided by its price than for the other goods, then of course we would want to buy this good because it would increase our objective function by more than if we spend the money on any other good. So we would do this in a way that at the optimum we could not reallocate a certain budget between the different goods and thereby increase our utility, because if we could, then the initial choice would not have been optimal in the first place, and the necessary first order conditions from the utility maximization problem would have been violated in this case. And now translated into everyday language, this tells us nothing else than you should buy the stuff you like unless it is too expensive because the price is high. And after all, this is a pretty standard behavior actually. So it's not completely weird to assume that most individuals behave in a way that they spend their money on things they like, unless these things are overly expensive. Step 3 of the cookbook procedure is to solve the system of equations that are given by the necessary first order conditions. In our case of two choice variables, we could have three equations in the three unknowns of the two choice variables and the Lagrange multiplier. And that leads us directly to step 4, namely to analyze and discuss the solutions and to check whether they are global maxima or minima, or whether they are only local maxima or minima, or neither of that. So in step 3, we could basically get the result that we have no solution at all, that we have one unique solution, or that we have multiple solutions. Now, one common result in economics would be that we face a maximization problem in which the Lagrangian function is well behaved. That means it is strictly concave in case of maximization problems, or strictly convex in case of minimization problems. And in this case, the optimum is unique, and we would find one unique optimal point by solving this system of equations in three unknowns. Now, this is illustrated here by means of a utility maximization problem, where the utility function would be concave, so it would increase in the choice of a certain good, but the increase would level off basically. So that would be diminishing marginal utility from the consumption of good X. So the first unit of consumption would give high additional utility, so the marginal utility is very high for a low consumption level of X, but if I have more, then each additional unit of the consumption of X gives ever less additional utility. Now that's reasonable, and for most goods it would be a rather good approximation of how individuals behave in this sense. So think, for example, on food. If you are very hungry, the first unit of food increases utility by a lot, but if you have eaten already quite a lot, then each additional unit would give you less pleasure, and at some point it would flatten off. Now, if the utility function is of this concave form, and we have a linear budget constraints are typically linear, but they do not need to be linear, but typically they are. So if we subtract from this a linear budget constraint, as we would do by the construction of the Lagrangian function, just multiplied with the Lagrange multiplier, then we would get a strictly concave curve, the Lagrangian in the end, that would have one unique maximum, and this would be the unique global maximum to this optimization problem. And as I said, many problems in economics are structured in a way that this is the case, and when we have some prior knowledge um, on the shape of the utility function and the budget constraint, then we can basically already make a statement on whether the candidate point for the optimum that we have found by solving the necessary first order conditions is such a global maximum or minimum, and we do not in this case need to explicitly check the second order conditions for a maximum or a minimum. However, things could be more complicated, of course. So for example, the system of equations in the three unknowns x1 bar, x2 bar, and lambda could yield no solutions. And in this case, either the optimization problem itself would have no solution, or the constraint qualification could fail, which means that it is not binding for any of the items, and therefore we would always want to increase consumption of all the goods in case of a utility maximization problem. So in this case, there wouldn't be a solution to the system of equations. And then the system of equations can have multiple solutions, and it can lead to multiple candidate points for maxima and minima. In this case, we would need to check whether a certain candidate point is indeed a maximum or a minimum. And this is done by the so-called second order conditions that are needed to distinguish between local minima and local maxima. And they give actually the shape of the Lagrangian function around the optimal point. And that's in case of multidimensional optimization, typically a matrix, so the matrix of the second derivatives, or the bordered Hessian matrix that also contains the constraint. And from this matrix, we can judge whether the function at the optimal point is convex or concave. And if it is concave, then the candidate point that we have found is a maximum. And if it is convex, then the candidate point that we have found is a minimum. So this amounts to checking actually the definiteness of the bordered Hessian matrix, because this definiteness gives us the information of whether the Lagrangian function is convex or concave around the candidate point. And we have to do this for all the candidate points that we get by solving the system of equations, and also for all the points at the border of the domain. So if we look at here again a simplified picture where we have a Lagrangian function, a hypothetical one with multiple maxima and multiple minima, and say the domain goes from 0 to 4 here in x. So then we would need to check for all of these points whether they are a maximum or a minimum. So we have to check for all of these points the value of the bordered Hessian or the definiteness of the bordered Hessian matrix actually, and we would find out that at this point the matrix is positive definite. That means that this is convex here around this optimum, and therefore this is a local minimum. Here we would find that the bordered Hessian is negative definite, and therefore the function here is concave at this candidate point, and therefore the candidate point is a local maximum. Of course, this procedure tells us nothing about whether the candidate point is a global maximum or a global minimum. So in this case, it would not be the global minimum for the domain, while this here would be the global maximum for the domain. And then we also have to check actually at the borders of the domain. We plug in the candidate points for the solution and check which of these candidate points in the objective function lead to the highest and to the lowest values. And from this we would determine that actually this point here is a global maximum and this point here is a global minimum. So that's what we would need to do in this case in which the Lagrangian function is not that well behaved, to check whether the candidate points for an optimum are indeed local maxima or minima, or it might even be the case, it's not the case here, but it could be the case that a border solution is attained, so that the solution at the border of the domain yields the highest value or the lowest value at some point. So now we have actually all the ingredients to apply Lagrange's theorem to minimization and maximization problems. And therefore we consider an example here of a utility maximization problem under logarithmic utility. So that's the simplest case we can think of. And here we consider that a consumer can choose two goods, x1 and x2, and the prices of these goods are p1 and p2, and the consumer wants to maximize her utility under the constraint that it has a certain income level I, so that it cannot spend more than I on the consumption of the different goods here. So actually, by means of the theorem of Lagrange, we even have the situation that it must spend all the income. Later on, we will talk about the method of Karush-Kundaka, where it's also allowed that the individual might leave money at the table, so it does not need to spend the whole budget. However, now here we have an equality constraint, and the budget constraint is linear, as is the standard case in economic models typically, where we have the price of good 1 times the quantity of good 1 consumed plus the price of good 2 times the quantity of good 2 consumed must be equal to the income level. Non-linear constraints could be, for example, if there are rebates. If you consume a certain quantity and above a certain quantity, then the price itself might depend on the quantity, because you get the rebates if you consume a certain amount of the good. Then you would have non-linear constraints, but typically we deal with linear constraints. Now, because this is an example with logarithmic utility, the utility function is logarithmic, so we have a utility of consumption of the two goods x1 and x2 depends on the quantities of these two goods in a logarithmic manner. So we have that an increase in the consumption of good 1 increases utility, but again in a concave way. So the more we have of good 1 holding good 2 constant, the better the individual is off in terms of a higher utility level, but the increase in utility becomes smaller and smaller the larger x1 already is. And the same holds true for x2, and alpha and beta are the weights of these two consumption goods. So basically the taste, so the relative size gives the relative taste of the consumer with respect to good x1 and to good x2. So if alpha is higher, the person likes good 1 better, ceteris paribus, and if beta is higher, it likes good 2 more, ceteris paribus. And then we follow the steps of the cookbook procedure. So first, we set up the Lagrangian function. So we have the Lagrangian, depends on the choice of the two variables x1 and x2, and the Lagrange multiplier lambda. We plug in here the objective function, so alpha times the logarithm of good 1 plus beta times the logarithm of good 2 plus the Lagrange multiplier times the constraint, where we have the income minus the left-hand side of the constraint here, p1 times x1 minus p2 times x2. So that's the first step. In the second step, we follow the theorem of Lagrange and calculate the necessary first-order conditions. So we take the derivative of the Lagrangian function with respect to the choice variable 1 and set it equal to 0, we take the derivative of the Lagrangian function with respect to the second choice variable and set it equal to 0, and we take the derivative of the Lagrangian function with respect to the Lagrange multiplier and set it equal to 0. Now, with respect to the first choice variable, we see here that this is the derivative with respect to x1. So what we get here from this term is alpha divided by x1, because the derivative of the logarithm of x1 would be 1 over x1. Here x1 does not appear, so this term would drop out. And here x1 would appear multiplied by lambda times p1 with a negative sign, and that's exactly what we have here. Analogously, we would have the derivative of the Lagrange function with respect to x2. And if we take the derivative of the Lagrange function with respect to the Lagrange multiplier, then it's natural that the budget constraint survives, because here we see this is the budget constraint. If we take the derivative with respect to lambda, then the budget constraint remains there, and this has to be equal to 0, so the budget constraint has to be fulfilled. So these are the necessary first order conditions for this utility maximization problem. In the third step, we solve for the unknowns. There are many different ways we can do so. The one that is chosen by Dixit in his book is to isolate x1 and x2 from the first two equations. So isolate x1 from this equation and express it in terms of alpha, lambda, and p1, and isolate x2 from the second equation and express it in terms of beta, lambda, and p2, and then to plug in these results into the budget constraint here and solve for the Lagrange multiplier. And in this case, what he gets for the Lagrange multiplier, and what we get if we do the calculations here, is that it is a positive function of alpha and beta, so the two taste parameters in the utility function, and a negative function of income. And this is already the explicit solution, because these are only parameters. Now the interpretation is clear and straightforward. The effect of a relaxation, of a marginal relaxation of the constraint on the objective function, decreases if income of individuals is higher, becomes higher. And the reason is clear, because the utility function is logarithmic, so it's concave. So an additional increase in consumption that people can afford brings ever less additional utility. So therefore, the higher the income level, the lower would be the Lagrange multiplier, so the effect on the objective function of a further increase in income. And by contrast, if the two taste parameters are higher, that means the desire for the two goods x1 and x2 of the household is higher, then this would lead to a higher Lagrange multiplier, because the relaxation of the constraint would then yield a higher additional utility level. So that's already the solution. Then one can take lambda and plug it into the expressions for x1 and x2 that we've derived from equations 1 and 2 in the previous step. And if we do so, what we get is then the explicit solutions, the explicit demand functions for the good 1 and the good 2 here, expressed in terms of the parameters of the utility function, in terms of income, and in terms of the price of the corresponding good. Now, we would again see straightforward interpretation. If income increases, then individuals, households would consume more of both goods, actually, because they can afford more and they could spread the additional income on both goods. If the price of the corresponding good increases, so if P1 increases, households would consume less of good 1 because it becomes more expensive, and therefore they would choose to consume less. The same holds true for good 2. If the price of good 2 increases, consumption of good 2 would decrease. There are no cross effects of the price of good 2 on the consumption of good 1 and vice versa in this case, and the reason is the logarithmic utility here, where these cross effects cancel out. And then we have finally, if alpha increases, then households would increase consumption of good 1 and decrease consumption of good 2, because there is a taste shift towards consumption of good 1, so households would consume more of this good and less of the other. And exactly the opposite would hold true if beta increases. In this case, the households would decrease consumption of good 1 and increase consumption of good too. So all of these results have a straightforward and intuitive interpretation, and again, all of them are kind of consistent with standard behavior that we would expect of individuals, and they are not really surprising. And even if people do not stand in front of the shelf and maximize Lagrangians, they behave rather consistent with these effects. Well, and then we have step 4, and here we know that the objective function is strictly concave. It's a logarithmic utility function, and the constraint is linear, and therefore the Lagrangian will be a strictly concave function. So we subtract a linear function from a concave function, from a strictly concave function, and therefore the result is again strictly concave. So therefore we know that the candidate point for the maximum that we found is indeed a maximum, and it is indeed a global maximum. So in this case, the prior knowledge about the function, about the utility function and the constraint allows us to make these statements already without checking the second order condition.